Okay, so since nobody's joining, I will just continue on my own. Um, okay, so I did that in the previous session until here. No, until here. Okay, in addition to element-wise computations, we can also perform just check if the audio is working. Test, yeah. Okay. So, in addition to element-wise computation, we can also perform linear algebra operations, including vector dot products and matrix multiplication. We will explain the crucial bits of linear algebra with no assumed prior knowledge. In section 2.3. We can also concatenate multiple tensors together, stacking them end to end to form a larger tensor. We just need to provide a list of tensors and tell the system along which axis to concatenate. The example below shows what happens when we concatenate two matrices along rows. Axis 0, the first element of the shape, versus columns. Axis 1, the second element of the shape. We can see that the first output tensor's axis 0 length is the sum of the two input tensors' axis 0 length, while the second output tensor's axis 1 length is the sum of the two input tensors' axis 1 length. Torch 32. Why? 2, 3, 4, 3, 2, 1. Yeah. Torch cat is y actually 0. Torch cat xy. Wonder what's the difference between the dimensionality 0 and dimensionality 1. The example below shows what happens when we concatenate two matrices along rows. X is 0, the first element of the shape, versus columns. X is 1, the second element of the shape. You can see that the first output tensor's x is 0 length is the sum of the two input tensors x is 0 lengths. Okay, so the first output tensors x is 0 length is 6. 1, 2, 3, 4, 5, 6. And here it's 1, 2, 3. And this one also gives the 3 rows. Okay. So, okay. While the second output tensor's x is 1 length, 8 is the sum of the two input tensors x is 1 length. 4 plus 4. So the columns are here 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay. First input tensor is 1, 0, 1, 2, 3. Okay. 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 Maybe I should do some more tensor concatenation to get the hang of it. X1 torch arrange 4. E-type torch flow 32. Arrange 8. Reshape 1, 2. And then second one. They have to be the same size, I guess. So if I try this, torch tensor, 2, 4. And if I try concatenating, I guess it doesn't work. X, Y. Okay, so it has to be the same shape as the other input vector. And this one I can't reshape. But I could do like this, -1. And then this one needs to have 8 inputs. 3, 4, otherwise it won't work. This is not the same dimensionality. Oh, it works. Okay. Okay, let's look what this actually gives. Okay, so this gives a vector of dimensionality 8. And then it's possible to concatenate it with a vector of dimensionality 4. It's higher number to make it clear. 500. Oh, okay. Obviously, it doesn't work because I'm using the previous examples, x and y. This one should be 1, 2. Expected object of Scala type float, but that's Scala type long int for sequence element 1. Okay. Probably can't combine floats and integers. Okay, now I get the sizes of the tensors must match except in dimension 0. Got 8 and 4 in dimension 1. Okay, so for dimension 0, where it's concatenating, it doesn't matter because it's concatenating in dimension 0. Okay, I get it now. Okay, all right, start to get it. So what I could do, I could say arrange 4, and then here give another tensor at dimension 2 with even higher numbers, 2,000, 8,000, 4,000, 5,000. Now it should work actually. I need to rerun this cell. Yeah, okay. So let's actually see what happens if I concatenate at dimension 1. Torch cat x x1 2 dimension. Okay. So now they should match in size at dimension 1. Okay. Dimension 1. Wait. So now what I could be doing would be I could give here 600. And here I could let me check. Here I could create another one, the same dimensionality, which would be 2 in this case. So this obviously doesn't work anymore, but this works now. So it's here 0, 1, 2, 3 from this vector here, this tensor here, plus the 200, 300, 400, and 500. Okay, I get it now. Sometimes we want to construct a binary tensor via logical statements. Take x equals, or x should equal y as an example. For each position, if x and y are equal at that position, the corresponding entry in the new tensor takes a value of 1. Meaning that the logical statement x should be equal to y is true at that position. Otherwise, that position takes 0. Okay. Okay, so then we should get, I will delete this. And continue. X equals y. Yeah, because 0 in this input tensor, and wait. Okay, because yeah, I will remove this. So it's more clear. They're actually both of the same dimension. Both are 3 by 4, so 3 rows and 4 columns. Then 0 doesn't equal 2, so it's false. 1 does equal 1, so it's true, etc., etc. Okay. Summing all the elements in the tensor yields a tensor with only one element. Okay, so if I sum the tensors, x sum, I get 66. Okay. For stylistic convenience, we can write x sum as np sum x. Broadcasting, or chapter 2, section 1, subsection 3, broadcasting mechanism. In the above section, we saw how to perform element-wise operations on two tensors of the same shape. Under certain conditions, even when shapes differ, we can still perform element-wise operations by invoke the broadcasting mechanism. This mechanism works in the following way. First, expand one or both arrays by copying elements appropriately so that after this transformation, the two tensors have the same shape. Second, carry out the element-wise operations on the resulting arrays. In most cases, we broadcast along an axis where an array initially only has length 1, such as in the following example. Okay. A equals torch arrange 3, reshape 1, B equals torch arrange 2, reshape 1, 2. A, B. Okay. Since A and B are 3 by 1 and 1 by 2 matrices respectively, their shapes do not match up if we want to add them. We broadcast the entries of both matrices into a larger 3 by 2 matrix as follows. For matrix A, it replicates the columns, and for matrix B, it replicates the rows before adding up both element-wise. Okay. Tensor 1, 0, 1, 2, 2, 3. Okay. Okay, it's because it's doing a plus operation. Zero. Okay. So this is the same as Tensor. This is annoying. Zero. How do I get rid of this? Okay. 0, 1. 0, 1. 0. Two. Two, three. Okay. So this, the output should be the same. I guess that is what they mean by broadcasting. No, actually, it should be. I got distracted. Should be 0, 0, 1, 1, 2, 2. Yeah, that gives the same output as the addition via broadcasting tensors of differing dimensionality. Okay. Chapter 2.1 for indexing and slicing. Just as in any other Python array, elements in a tensor can be accessed by index. As in any Python array, the first element has index 0 and ranges are specified to include the first but before the last element. As in standard Python lists, we can access elements according to their relative position to the end of the list by using negative indices. Those square brackets -1 selects the last element, and square brackets 1:3 selects the second and the third element as follows. Okay. I'll create a big tensor. X equal to 40. Reshape 8, 8, -1. Session crashed. Okay. Name NP is not defined. I need to import num. I can use torch image. Okay, so I need to bring the wait. 8 by 8. 8 by 8 by 2, for example, wouldn't work. By 1 would work. I mean, it's 64. How does that work? 8 by -1 would work. Why does it crash? Oh, it doesn't crash. I just need to output this. Okay. Is it invalid? The -1, it shouldn't be invalid with the -1. How if I try 64? And then 8 by 8. So that works. What if I try 8 by 7? That shouldn't work. Okay, what if I try 8 by 8 by 8? And then I multiply this by 8. This works. Okay, I will just use this. Okay, I don't know why, but so x -1 should be the last element. So this And then if I try the x3, should return 64. 2, 3 until 255. No, wait. 64. This is 1. This is 2. This is 3. So this is the 0th. And first, second, third. Oh, okay. It's not inclusive. It's not. It's an exclusive range. Okay. Okay. Second and third. Okay. Beyond reading, you can also write elements of a matrix by specifying indices. So I could say 1, and for simplicity, I say 0, 0, 0, so that should change the 64 to 32. Output X. Yeah, as expected, okay. If we want to assign multiple elements with same value, we simply index all of them and then assign them the value. For instance, 0 up until the second element. Where just colon takes all the elements along axis 1 column. Okay. So if I do that, I made a text so I can x 0 second element, set it to 12, then output x. So what this should do is this, it should set, wait, yeah, this and that elements and it would all set all of these to 12. Yeah, I guess it would replace all of the arrays here by 12. Yeah, okay. Chapter 2, Section 1, Subsection 5, Saving Memory. Running operations can cause new memory to be allocated to host results. For example, if we write y equals x plus y, we will dereference the tensor that y used to point to and instead point y at the newly allocated memory. In the following example, we demonstrate this with Python's id function, which gives us the exact address of the referenced object in memory. After running y equals y plus x, we will find that id of y points to a different location. That is because Python first evaluates y plus x allocating new memory for the result, and then makes y point to this new location in memory. Before, I don't know, how do we even have a y? No. So let's say y equals tensor dot, sorry, not tensor, torch dot array 100. Then we say before id of y equals y plus x, id of y is before, and also I want to see the before and the id of time. Let's just create a new x. Okay, false, and they indeed differ. Okay. This might be undesirable for two reasons. First, we do not want to run around allocating memory unnecessarily all the time. In machine learning, we might have hundreds of megabytes of parameters and update them, all of them, multiple times per second. Typically, we will want to perform these updates in place. Second, we might point at the same parameters from multiple variables. If we do not update in place, other references will still point to the old memory location, making it possible for parts of our code to inadvertently reference stale parameters. Fortunately, performing in-place operations in MXNet is easy. Okay, so there's no part for PyTorch. Okay. You can assign the result of an operation to a previously allocated array with slice notation. Meaning, for example, y of all rows, or yeah, y of all set all rows of y to expression. To illustrate this concept, we first create a new matrix Z with the same shape as another Y, using zeros like to allocate a block of 0 entries. I'll have to get something to eat. Pause this. So actually I will wrap it up right here. It's also almost finish of this session. If you want to join the next session or join these sessions, they happen daily at multiple time slots. And you can go to 247reading.group and you can click this link at the top to join the meetup on meetup.com, and you'll be notified about all events.